Okay, David, it's time to start. So let me, okay, so good morning, good afternoon, and good evening, everybody. Welcome to this APCTP colloquium. Today we have Professor David Huse as a speaker, and my name is Jae-dong No, and chairing this morning's the colloquium. So let me first briefly introduce Professor David Huse. Okay. So he started to learn physics at the University of Massachusetts in 1975 and got his PhD degree in 1983 at Cornell University under the supervision of Micklitz Fisher. And since then, he worked at Bell Lab from 82 to 96. And now he is serving as a professor of physics at Princeton University since 1996. And also he is also affiliated as a visiting associated member at Institute for Advanced Studies since 2010. And since 1978, he published over 250 papers in peer-reviewed journals, primarily in theoretical condensed matter and statistical and quantum physics. Actually, he has a very broad research interest, and for example, the topic includes from phase transitions and superconductivity, spin glasses and random magnets, biophysics, to quantum many-body physics of ultra-cold atoms, magnetic materials, and spin liquids, localization, chaos, thermalization, entanglement, and quantum codes. As a recognition of his impactful scientific activity, he got the last Onset Prize from American Physical Society in 2022. So finally, I would like just one remark. He is an excellent speaker, so I am pretty sure that everyone will enjoy his presentation today. So it's time for David. Okay, please go ahead.
Okay, let me share my screen.
And if someone want to ask a question, just interrupt and feel free to ask a question during his talk.
Okay, that's visible, I hope.
Yes.
And this cursor.
Yes, that's visible, I hope.
Hand is visible. Okay.
Yes, good. Yes.
Okay. Thank you. So today, what I'm going to tell you about is some thermalization transitions, really, in some sense, phase transitions in closed many-body quantum systems. And I saw in your program of this colloquium that recently Mark Trednicki gave a talk. So you've been, at least those of you who were at his talk as well, a little bit prepared about having heard things about thermalization. But I'm actually going to talk about different kinds of thermalization as well as transitions from non-thermalizing behavior to thermalizing behavior. Okay, so this is about, as I said, closed many-body quantum systems. So we have, I sort of draw that as a little box here with walls around it. It's isolated from any environment. And inside of this box, we have a large number of quantum degrees of freedom, not infinity, some finite number. We're interested in finite numbers, but large compared to one. And these could be qubits or cold atoms or any quantum degrees of freedom. And nowadays there's lots of different systems where this situation is well approximated to some extent in the laboratory with various types of systems that are many-body atomic physics, or the kinds of systems people build to explore possibilities in quantum computation. So there are such experiments. And then also people are interested in these kinds of problems and do numerics on classical computers to learn about such systems. So I'm interested in so there's a lot of interest in these questions for these reasons. People are exploring it both in the laboratory and in computation and theoretically. Okay. Now, when I say closed, I don't mean it's not being driven by something external, but if it's being driven by something external, it's effectively a classical drive or a coherent state that the system is not getting entangled with. So the dynamics of our system is unitary, and it's given by a Hamiltonian, which might have some time dependence. Okay. And then thermalization is a question about what is the long time behavior of this system. In the limit of long time, does it successfully act as a bath for itself and bring all of its small subsystems to thermal equilibrium with each other? That's really what thermalization is the system is being a bath for itself, for its own subsystems. And if, say, there's conserved energy, then there's a temperature, and they're all brought to equilibrium at the same temperature, with the rest of the system acting as the bath. Okay. So there's two cases I'm going to be talking about. One is a time-independent Hamiltonian. Then it really can be a closed, isolated system with nothing outside doing anything. And when that's the case, you have a conserved energy because H is time independent. And so you would have a conserved energy, and it would be, if we take a large system, it's an extensive energy. And the thermodynamics of equilibrium is set by what that energy is. And you have eigenstates, which are stationary states of the dynamics, which are the eigenstates of the Hamiltonian. And in addition to the conserved energy, you might have some other conserved quantities like particle number or a spin or something like that. Okay, so that's one case, time-independent Hamiltonian. But I'll also be talking about Floquet systems, where instead of having a time-independent Hamiltonian, the Hamiltonian is periodic in time, but the system is being externally driven by, say, some oscillating fields or some pulses. And such Floquet systems are often set up because with those periodic drives or pulses, you can engineer the effective Hamiltonian to be something that's hard to make as a time-independent Hamiltonian in that particular experimental system. So a lot of these experimental systems that people are working with, very often their dynamics is Floquet, meaning the system is driven, but periodically in time. Okay, and when you have a Floquet system like this, then there is a unitary operator, which I'll call U sub F, F for Floquet, which is the unitary operator that advances time by one period of this drive. And I'll say more about that later. And then it's that gives the dynamics, the stroboscopic dynamics, meaning the dynamics after a full period. It's a unitary operator, so its eigenstates have eigenvalues which are of magnitude 1. They're just exponential of I times a phase. But by analogy to time-independent Hamiltonians, we can write that phase as this e to the I minus I and energy times the time. But because this eigenvalues on the unit circle, this energy times time is only defined modulo 2 pi. And so we have this quasi-energy, E sub n, which is a way of describing the eigenvalue of the Floquet operator for an eigenstate. And it's between, well, we can choose it to be between minus pi over the period and plus pi over the period. So that's often called a quasi-energy, and it's not extensive, right? Because it's, it's if we keep the period fixed and take a larger system, the range of the energy doesn't grow. It just remains 2 pi over tau. Now, a Floquet system, because it doesn't have a time-independent Hamiltonian, it doesn't have an extensive conserved energy. It only has this energy that's bounded, quasi-energy that's bounded, and it can have no extensive conserved quantities. And so sometimes when we're looking at sort of the fundamentals of unitary quantum dynamics, and we don't want to be distracted by conservation laws and transport and things like that, we like Floquet systems because they only have the physics of unitary dynamics, and you don't have the physics of or you can choose Floquet systems where you don't have the physics of conservation laws and transport. Okay. Now, right. So say, just to repeat about thermalization. So if we have thermalization of our system, which could be a Floquet system or a time-independent Hamiltonian, thermalization means the eigenstates as well as the typical long-time states. So thermalization sort of has two aspects. The dynamically, you start the system out of equilibrium, it goes to equilibrium. And then along with that comes the eigenstates are in equilibrium. Right. So if we have thermalization, both the eigenstates and the typical long-time states starting from a non-equilibrium initial condition are thermal. And again, by thermal, I mean all small subsystems are at thermal equilibrium with each other. And this so I'm going to use thermalization to be where there's only a few extensive conserved quantities setting the thermodynamic conditions, such as a temperature associated with the extensive conserved energy, chemical potentials associated with any extensive conserved particle number. Okay. And most quantum many-body systems, if isolated and you wait long enough, they do thermalize. But there are exceptions, right? And that's
a simple question.
Yeah, go ahead.
Yeah. What do you mean typical? Typical long-time states. What do you mean typical?
Well, I put typical because of the issue of recurrences. So if you start with a non-equilibrium, if you have a finite quantum system, so I want to say things that are true also for finite quantum systems. And if you have a finite quantum system, right, it's only got a certain number of eigenstates, and its behavior ultimately is quasi-periodic. And the initial condition, if you wait, many times the age of the universe, maybe it will recur, right? So the system, a finite system that thermalizes almost all times, it's near thermal equilibrium, but it will have occasional large deviations if it's a finite system, right? And so that's why I said typical. What I mean is at typical times.
I see. So Poincare recurrence theorem is proven in quantum mechanical systems.
Well, it's not Poincare recurrence, but the dynamics is just every eigenstate picks up a phase. That's what quantum dynamics is. You just take your initial state, write it in terms of the eigenstates, they all pick up phases, right?
Yes.
And there will be times in the very far future where all those phases come back very close to what they were at the beginning, just by chance, right? And that's a quantum recurrence. It's different than a Poincare recurrence, yes, which is about classical systems, but it does occur. So this is a technical point, but that's what I mean. I could have said long-time states at almost all times. That might have been a better way to say it. Right?
Okay, thank you. Yeah.
Because you can have special things happening. Yeah. Okay. Now, okay, so some exceptions to thermalization. So two of the big ones that I'm going to talk about today are integrable systems and many-body localization. And these are both cases where it's not thermalizing because there's an extensive number of conservation laws. And when I say thermalization, what I mean is thermalization with just a small number of conservation laws. And so the initial condition has an extensive number of specific things which are conserved that the system never forgets, right? And so that's one way of getting not full thermalization, right? And now the other thing I want to talk about, if I have time, is about the Floquet systems, where you can have two types of thermalization. You can have what's called the pre-thermal regime, where they're actually, although energy isn't strictly conserved because the system is driven, there is an emergent, extensive, conserved, effective Hamiltonian, so that the system does act like it has a time-independent Hamiltonian, even though it really doesn't. And then there's a phase transition to another regime where it heats up and the energy is only conserved modulo the frequency of the drive. And I'll talk about that. So those are the two subjects for today. Now, there are other exceptions to thermalization. One which has received a lot of attention recently is quantum many-body scars. I just mention it just because it's there and there's a lot of papers, but I will not discuss it. And there's other exceptions, things having to do with various kinds of constrained systems, Hilbert space fragmentation, things like that. But today I'm just going to talk about the Floquet. Well, first the integrable systems and how they transition to becoming chaotic and fully thermalizing, and then Floquet systems. Okay, now an important point I want to make is that the distinctions between thermalization and these exceptions to thermalization, such as integrability, which is what I'm going to talk about next, these are dynamical distinctions, and they're not thermodynamic. So the transitions I'm talking about are not changes in the thermodynamics. They're changes in whether the system relaxes to thermodynamic equilibrium, but it's a dynamical question. Now, as we know for thermodynamic phase transitions, if you want to make sharp distinctions between the phases and have the phase transition be a sharp thing rather than something that's more of a crossover, you have to take the limit of a large system and also infinite time in order to really equilibrate. Okay. Now here, for these transitions, it's the same, right? To really make the distinctions sharp, we have to take the large system limit. But because we're not talking about thermodynamic distinctions, only dynamical distinctions, the limit that you take when you take the large system limit can be different from the thermodynamic limit, okay? So I'm going to be telling you about some phase transitions that occur in a large system limit, but it's not the thermodynamic limit. Okay. And another point associated with this is that a change to your Hamiltonian or your, time-dependent Hamiltonian, that is dynamically important in determining thermalization, whether the system thermalizes or not, may be thermodynamically insignificant in the large system limit. And that's true in the example I'm going to give, in the examples I'm going to tell you right now about integrable systems. Okay, so now I'm going to start with a real textbook example of this. Actually, let me just pause, ask if there's any questions before I dive into this specific example.
Will you show me the previous page?
Yeah.
So, frankly speaking, I think I didn't catch the message in the last sentence. I mean, so will you just repeat and what does it mean?
Yeah, well,
Or
the
change to it,
example,
yeah.
the example I'm about to give you will illustrate this. But the statement is that you can have a term in the Hamiltonian that is dynamically important, and its magnitude on a certain scale determines, does this system thermalize, or does it, say, remain integrable or near integrable? But that term might be so small that it's thermodynamically just insignificant. So it has no effect on the thermodynamics, but it has a big effect on the dynamics. And that will be true in the example I'm about to show you.
May I ask you one question?
Yeah, please.
Just to clarify what you have just said, do you mean that basically you can add some microscopic perturbation and that can drastically change the thermalization dynamics? Is that what
Yes,
you're implying?
yes, yes. I'm
Okay,
gonna.
thank you very much.
Yeah,
That's very amazing.
Yeah. And this you have seen, although it's never really done. You know, this is what I'm going to tell you about in this example. It's really literally a textbook example. It's not right. So the way so there's this paper by Altshuler, Geffen, Kamenev, Levitov, 1997, who did this for. They were thinking of quantum dots, and they did this for. They were thinking of metallic quantum dots at low temperatures, and so they were doing it for the degenerate Fermi gas. But their arguments work perfectly fine for dilute gas. So we can go to the textbook case of just a dilute gas with very weak interactions, and not in a quantum degenerate regime. So that's what I'm going to tell you about. So dilute, weakly interacting gas. Dilute meaning it's not quantum degenerate, weakly interacting. But I'm going to follow what they did, even though they didn't do the dilute case. Okay. And I literally mean the textbook example, near ideal gas. So we have n particles in a volume V, and let's fix the density number. So a little n, my little n is going to be the number density. So when we take, we're doing a finite system, but when we do take the limit of a large system, we're going to take the limit with the density fixed and the temperature fixed. Okay. Now, the gas is quantum, right? That we in class talk a lot about classical gases, but the world is quantum. All gases are quantum. Can be in a regime where they're well approximated by a classical gas, if you don't worry about their dynamics. But all gases are quantum, even at high temperatures, and even when dilute, and even when in the regime where classical ideal gas theory is a good approximation for many of their properties. But of course, they're quantum because the world is quantum. Now, so I'm going to put this gas in a. I don't like having extra symmetries around, so I'm going to put it in a irregular box. So I drew this funny shaped box here, hard walls. We could put it in some trapping potential, but not something with any symmetry. And it's in 2 dimensions or 3 dimensions. So the single particle eigenstates. So before we turn on the interactions between the particles, I want the single particle eigenstates to be quantum chaotic. No symmetries or selection rules on the scattering. But I don't want single particle Anderson localization. So it's just like, if I just have, what they call a billiard, hard walls with an irregular shape, the single particle eigenstates will fill the box, but they'll be chaotic, right? So let's think of hard walls as the example with an irregular shape, okay? Now, if we have 0 interactions, this is an integrable system, right? It's a very simple integrable system, right? So let's C dagger alpha be the creation operator for a particle in single particle eigenstate alpha. And then n sub alpha is the occupation number of that single particle state. And if I have no interactions and I just have this box, each one of these n alphas for all the single particle state is a conserved operator, right? Because if I put a particle in that state, it's an eigenstate and it'll stay there. Okay. So this is an integrable system. It has an extensive number of conserved quantities, which are just the occupation numbers of each single particle eigenstate. And then the many-body Fock states are the simultaneous eigenstates of all these occupation numbers. So a many-body Fock state is for every single particle state, I tell you how many particles are in it. Right? And if it's fermions, it's either 0 or 1, and if it's bosons, it can go above 1. But I'm working in the non-degenerate regime, so the differences between fermions and bosons will not be significant in anything I tell you. Okay, so now we're going to add weak short-range interactions between the particles. And then, the standard thing you would say in your statistical mechanics class, oh, all I have to do is some weak interactions, and then this will thermalize, and it'll go to equilibrium and obey the Odile gas law, et cetera, right? And they don't actually do the calculation of how quickly does it thermalize, et cetera. And that's what I'm telling you about today. Okay, so here's now the many-body Hamiltonian in second quantized notation. I've got this weak short-range interaction. I give it interaction strength G. I've got it scaled, so V is the volume. I've got it scaled so that fixed G, taking the large system limit, keeping G fixed, is the usual thermodynamic limit, right? And that gives you this V to the 3/2 out front here. Okay, and here's the scattering process, right? So here's an interaction, right? Particle in state gamma and a particle in state delta interact and scatter into state alpha and beta. So they come in gamma and delta, scatter, go into alpha and beta. Now, if we have these, if the single particle states in this box are chaotic, then these matrix elements, all these eigenstates fill the box, they all overlap, they're they're pseudo-random states. And so these matrix elements for the scattering are just pseudo-random numbers. And let's say, pick a thing so that this U is of order 1, and the strength of the interaction is this G over V to the 3/2. Right? So whatever the strength of the interaction is, that gives me G, and then the V to the 3/2 is just to have things scale properly with the volume. Okay. So this is just standard interacting particles. Okay. Now, remember, my Fock states are the eigenstates of these occupation numbers. So this term, the single particle energy, is diagonal in the Fock states because it just contains the conserved quantities for the Fock states. But this term here, which scatters, is off diagonal. It scatters from one Fock state to another Fock state. It removes 2 particles from gamma and delta and puts them in alpha and beta instead. So that's going to a different Fock state. So this is off diagonal in Fock space, but it's short range in Fock space because it only changes 4 of these occupation numbers, right? There are n, if there's n particles, there are n, well, for at least, there are n, there are of order V single particle states which have occupation numbers, which is a large number, and we're only changing 4 of them, right? So in that sense, it's short range in Fock space. So this is a diagonal term, and this is a hopping term in Fock space. Okay. So the transition from being actually near integrable to thermalizing, which is discussed by AGKL, Altschuler and company, what you have is if this scattering is too weak, it can't cause transitions among Fock states, and the eigenstates of this Hamiltonian remain localized like they are at G equals 0, and the system stays in a phase that I call near integrable, right? It's not exactly integrable, but the perturbation to integrability is too small to thermalize the system. And then when the scattering is strong enough, the system thermalizes, it goes into, it becomes quantum many-body chaotic, right? We already had single particle chaos, but then it becomes, when G is strong enough, it makes many particle chaos. And this happens at larger G. And then the eigenstates of this Hamiltonian become delocalized in Fock space. So this transition is a Anderson localization transition in the Fock space between localized and delocalized. The transition happens at some coupling. But then if you take the limit of a large system, fixing N and T, and then if I want to see the transition, I need to scale my coupling by the critical coupling, which depends on the volume. And if I take the limit that way, which will take the critical coupling to 0 as the volume goes to infinity and the number of particles goes to infinity, then I can see this phase transition. So this is not the thermodynamic limit. This is the appropriate limit to see this dynamical phase transition. But in this limit, since the critical coupling goes to 0, thermodynamically, we get a non-interacting gas in the limit. But dynamically, it's an interacting gas, and it has a transition from not thermalizing to thermalizing. Okay, so let's now make that estimate. Actually, maybe I'll pause here. Questions. So I haven't. I'm gonna show you how GC behaves as a function of volume.
Yeah. So, frankly speaking, yeah. Still. So, will you explain more about this limit? I think so.
Yeah, I will.
One more question is, if I solve this problem in the Hartree form, just mean field decomposition for the interaction term, then can I see this behavior in the single particle basis?
I don't think so. Well, this is about dynamics, so it would have to be a dynamic Hartree-Fock, that really does the dynamics.
Yes, time-dependent Hartree form, for example. Yeah.
That's a good, that I don't know whether this can be seen by doing time-dependent Hartree-Fock in the appropriate way. Yeah, I'm not sure. I haven't actually thought about that.
Okay, yeah, thank you.
Okay, so here's our Hamiltonian again. And this fact, as I said, this factor of v to the 3/2 on the bottom here is such that if I want to take the thermodynamic limit, what I do is I hold G constant and not 0 nor infinity. So it's an interacting gas, and then take the limit of an infinite system with fixed density and fixed temperature, right? And that'll give you the interacting gas in the thermodynamic limit. And that system does thermalize, right? So the interacting gas does thermalize. So in that sense, in your statistical mechanics class, it's correct to say all I have to do is put some interaction and the system will thermalize, right? As long as you keep the interaction at a fixed value as you take the thermodynamic limit, you end up in the thermalizing regime. Okay, but let's make our first estimate of how the critical value of the interaction scales as we change the volume, change the size of the system. Okay, so what I'm going to do now, I'm going to, remember, I'm going to set scales. So the density is 1. I'm going to keep that fixed. The temperature is 1, and let's just keep the mass 1. So this is a way of fixing all the units and making everything dimensionless. It's not the usual thing of setting h bar equal to 1, okay? So if we do this, then h bar is the ratio of the thermal de Broglie wavelength to the particle spacing. So if we're in the dilute non-degenerate gas, Planck's constant is less than 1, whereas if we do the degenerate case, like AGKL did fermions at low temperatures compared to the Fermi temperature, and that would, in this convention of scaling things, that would correspond to large h bar. And I'm not going to talk about the large h bar regime. I'm just going to do the h bar less than 1 regime where the behavior is the same for fermions and bosons. The quantum physics is being put in, but the quantum statistics is unimportant in this regime. Okay, so let's consider an initial Fock state. So I'll call it phi. It's a Fock state, so each occupation of a single particle state is an integer. If we're in this regime of non-degenerate, most of those integers are 0, a few of them are 1. If it's bosons, maybe there's a few 2 or 3, but mostly it's just a lot of zeros and a few ones. Okay, and let's just assume phi is a typical Fock state at thermal equilibrium at these conditions: density 1, temperature 1. Now the Fock state is not thermal, right? A thermal state would have the probability distribution of the occupation number being either the Fermi direct distribution or the Bose-Einstein distribution or the Boltzmann distribution. It wouldn't be fixed at 1 integer, right? So phi is not a thermal state, okay? It's a particular initial state with particular states occupied and particular states empty, right? Now, the scattering matrix elements up here of this scattering operator here will, at first order, you can scatter from this state phi to of order v to the 4th, and if you put in the factors of h bar to the 2d on the bottom here, other Fock states. So you make this transition, n alpha goes to n alpha plus 1, n beta goes to n beta plus 1, and gamma goes to n gamma minus 1, and delta goes to n delta minus 1. So the v to the 4th comes because I can pick 4 different occupation numbers to change, and the number of possible occupation numbers to play with at temperature 1 is proportional to the volume. And then if you think through it carefully, you can figure out the h bar is there then, and it makes sense. In the dilute limit, there's more states to scatter to because there's so many empty states, right? So alpha and beta are typically empty, and you can scatter into them. And the more dilute your gas is, the more states you can scatter into. And that's why h bar is on the bottom here, right? And this is counting the number of Fock states with a change of energy that's just of order 1, right? Because we're really only thinking about the single particle states with energy of order 1 because we're talking about temperature of order 1. The states at much higher energy, they're not playing an important role because their occupation is so low. Okay, so now we're going to look at this, what I just told you here. So here's our initial state. So this is energy. Here's this initial Fock state, and there's its diagonal energy. So I'm drawing the diagonal part of the energy. And here's all these other states that it can scatter to at first order in perturbation theory, right? And they range over an energy of order 1. And there's many of them in the limit of a large volume. So remember, there was v to the 4th of them. And so it's a near continuum, right? But it's not really a continuum, right? We're talking about a finite system. And so this is a discrete set of states that this initial state is coupled to, right? And they have a level spacing, which is Planck's constant to the 2d divided by v to the 4th. Right? Because there's v to the 4th over Planck's constant, the 2d states ranged over an energy range of order 1. Now, this situation here of a single state coupled to a near continuum, which isn't a continuum, it's actually discrete, is something we analyzed in this recent paper here with my student Alan Morningstar, Alex Altland, and Tobias Micklitz, where you can actually, this is a problem in random matrix theory. You can say, oh, what if these are the states of a random matrix? And then we add another level and couple it very weakly to the random matrix. When does it decay? When does it not decay? And you can actually solve all of that stuff exactly. So that's just an aside, advertising this paper. Okay, so the matrix elements that couple my initial state to each one of these states in this near continuum are G over V to the 3/2. Remember, that's right here. These are just of order 1, right? So they're of that order. They're random, but they're of that order, right? So this is the matrix element coupling. This is the level spacing. Now, if the level spacing is much bigger than the matrix element, then typically there won't be another state degenerate, close to degenerate on this scale with my initial state. And the system will just be stuck in the initial state and it can't do anything. There's no states close enough by in energy for it to scatter into. So although there's a matrix element for the scattering, the states it wants to scatter into are too far away in energy, and the matrix element isn't strong enough to make that happen. And that's the regime where the system stays localized in Fock space. So if this matrix element is small compared to this level spacing, the system won't thermalize. So for this initial state to mix with and decay to this near continuum, you need this to be of order this or bigger. So you need this condition here. And so that tells you that the critical coupling in order to get thermalization scales like this. So it's got h bar to the 2d and it's got volume to the 5/2 on the bottom. So you see, as I go to the limit of a large system, this coupling does go to 0. Right? Now you also see that as I take the limit of a dilute gas, which is essentially classical, and h bar goes to 0, this coupling goes to 0, right? And we know the classical system will thermalize, with any interaction. It's only quantum mechanically that you have a threshold. Okay. Now, if you do this, a more careful analysis of this kind of Fock space Anderson localization, this is really an Anderson localization problem, where you've got this Fock space, you have diagonal energies, and then you have hoppings, right? And are the eigenstates Anderson localized or not? And there was an old paper, Abu Chakra, Thallis, and Anderson's 50 years ago, which shows that this estimate, if you do it carefully, there's an extra logarithm, right? But that's not, we already have this v to the 5/2, and so we put an extra logarithm. That's not a big deal. But if you really do it carefully, there's an extra logarithm. Due to higher order processes, is actually, it delocalizes a little bit earlier than what I said because of higher order processes. So this sets the interaction where the transition to thermalization happens in this textbook case. So when the gas is quantum and finite size, you have to turn on the interaction strong enough in order to get it to thermalize. Otherwise, it can't scatter because of the discreteness of the spectrum.
Excuse me.
Yep.
Can you show me the previous slide? So here, 3/2, the exponent 3/2 is coming from, to make the energy extensive in volume, right?
Yeah, right. If we do the conventional thing where the interaction strength of order 1 corresponds to something that is thermodynamically of order 1, then you end up with a v to the 3/2 on the bottom here.
Okay,
so
so
that's sort of standard stuff, because the eigenstates, the single particle eigenstates we're talking about are delocalized over the whole volume, and so their amplitude at any one place is 1 over square root of volume. And it's those factors that go into that.
And then here you kind of count, I mean, the estimate the level spacing from your interaction Hamiltonian, and then you have exponent 4, 3 to the 4. And what happens if you imagine some restricted interaction, not free interaction in the Fock space, but with some selection rules, every Fock state can interact with each other, but only some partial set can interact. Then you can tune.
Yeah, like for example, I could have put periodic boundary conditions and had momentum conservation. But I think if we, well, I'm not positive about that, but that will make, because of the momentum conservation, the coupling of the transitions that can happen will be not v to the 3/2, but it'll be a different power of v, right? That, and also the number of different states you can scatter into would be a different power of v. And I think, although I'm not going to insist, that you end up with the same result in terms of v to the 5/2, but I'm not going to insist on that.
Okay.
But I think that's the case. But yeah, if you have extra conservation laws and selection rules, these things do change. But the precise powers aren't actually the important thing here. It's that there is a threshold, which is a power of the volume, and it goes to 0 as the volume goes to infinity. And certainly that will stay true. The precise power might change. And you can make different models with different powers there, but it's always, the coupling is going to 0 as a power of v.
You mean, even with some extra conservation, still you expect the critical value of GC will decay to 0 in...
Yeah, as a power of v. Yeah.
Okay, please go ahead. Thank you.
Related question, if I consider some degeneracy in P state, so what will happen? Degeneracy in P, not only single state P. So
Degeneracy, right. I'm sort of implicit, like if we have a chaotic box like that, you're not going to have, the chance of having a precise degeneracy is 0. Again, I think details will change, but I don't think there will be qualitative changes associated with, of course, if I did the periodic boundary conditions, I would have degeneracies, right? Because plus k and minus k would be degenerate. But I don't think it's going to qualitatively change things. But like I said, I deliberately, did the case where it didn't have that stuff, in order to, focus on the essence of it, right? And right. If you put in extra conservation laws or extra symmetries, then there's more things you have to worry about here. But I don't think there's any case where, if the system, right, of course, it could be a one-dimensional system, and I could put in an interaction such that even with the interaction, it's still integrable, right? There are one-dimensional systems with interactions which are integrable, right? And then, of course, this argument isn't correct. But if it's in 2 or 3 dimensions, I'm not aware that there's any models where you just add an interaction between particles and it stays integrable.
Thank you.
I have one more related question. What happens if the interaction is long range instead of contact? Will there be any qualitative change?
Yeah, again, if it's long enough range, some of these exponents will change. But I'm not aware that the basic statement that we have a critical coupling where you transition from integrability to thermalization and chaos, and that coupling is going as 1 over a power of the volume. I think that's a very robust conclusion to all these kinds of changes.
Thank you.
Yeah. Okay, so let's take the limit v goes to infinity with g over gc of v fixed, right? So we get an estimate of gc of v. Now, in the finite volume, if v is finite, this gc isn't really a sharp transition, right? It's only in the limit that it sharpens up to a transition where there really is a sharp distinction between these two phases, as is standard with phase transitions. But this isn't a thermodynamic phase transition, this is a dynamical phase transition, but it's similar. And so you end up with this phase diagram like this, where, you know, because it's g over gc of v, the transition is at 1 by definition. And so here we have the non-interacting problem. Here we have a system which is interacting, so it's not fully localized on the Fock states, but the scattering is too weak to delocalize it in Fock space, and the eigenstates remain localized in Fock space, not strictly localized on one Fock state, but like in Anderson localization, localized near a Fock state with tails decaying as you go away. Right, and then beyond the transition, the system becomes delocalized. You know, this eigenstates will be delocalized in Fock space, or an initial state will wander off in Fock space and thermalize. Now, since at the transition, we have this level spacing going as h bar to the 2d over v to the 4th, and that's the characteristic energy scale associated with this. You have a characteristic, you know, if we just convert that to a time, the characteristic time near the transition is going as v to the 4th over this with, you know, one less power of h bar in order to convert it to a time, an energy to a time. So this is long. So as we take the limit of a large system, this is long, but only power law long, right? Whereas if you ask about the Heisenberg time, which is the time scale set by the level spacing between all many-body states, of which there are exponentially many in the volume, then the Heisenberg time is exponential in the volume. So, so although this is an effect happening on a long time scale, this localization, delocalization transition, it's not on the longest time scale in the system. It's on a time scale much shorter than the longest time scale in the system. Okay, so that's the textbook example. So what I'm telling you, right, and then the other point is that this interaction, since it's going down as v to the 5 halves, when I take the limit of a large system, it's really going to 0. So it's thermodynamically something which goes away, right? The thermodynamic effect of the interaction is going down as v to the 5 halves, and so it's gone in the limit. Even though, right, so sorry. So if I'm here, say in this phase here at, say 3/4, I'm in this regime that remains localized. Sorry, I should say it. Yeah, no, let's say we're just above the transition here at 1.5. The system does thermalize. The interactions are strong enough to make it thermalize and have very different behavior than it has over here. But those interactions are thermodynamically insignificant, right? In the limit of a large system, they have no effect on the thermodynamics because they're down by this power of the volume. Right. Okay. So I was telling you about that simple case of the non-interacting, well, sorry, of a dilute gas with weak interactions, as as a sort of warm-up to talk about more general integrable systems, where this calculation is much less complete. So let's now consider interacting integrable systems, right? So integrable systems that are not so simple as the one I just told you about, which was a non-interacting gas. Okay, and so we have this paper, so with Bulchandani and Gopalakrishnan, we had this paper last year considering this. And so let's say, it's a strongly interacting integrable system, say Liebling gas, which is a one-dimensional Bose gas with contact interactions, or some other beta ansatz solvable model, which are pretty much all in one dimension, or there's also these higher dimensional quantum dot kind of models, Gaudin, Richardson, where there's various integrable models which are understood and have similar kinds of solutions as beta ansatz. So there are many kinds of interacting integrable systems that are known, and there's a lot of technology to learn things about them, but not everything. Okay, but say now we have an and these integrable systems, they have the property that they have an infinite number, or they have an extensive number of conservation laws, so they don't really fully thermalize, or they thermalize in their own way with an infinite number of conservation laws to what's called a generalized Gibbs ensemble. But I'm just going to call that not thermalizing. Okay, and then we're going to add a term that breaks the integrability. So here's my Hamiltonian, here's my integrable system. So that's an integrable Hamiltonian, which doesn't thermalize. It's not quantum chaotic. Here's my coupling constant. And then I add another term, generic term that breaks the integrability, leaves only maybe one, maybe it just leaves one conservation law, the total energy, right? Or it might leave more than one, but just order one. And, a simple example would be, this might be a random potential. So adding randomness to the terms that are already, most integrable systems, if I just add local randomness to the terms in the Hamiltonian, that breaks the integrability, right? Because the integrability has to do with detailed solution of Yang-Baxter equations, and they require all the coefficients to be right. So I want to put a kind of a generic integrability breaking term. Okay, and so now we're going to do like we did before, but now our Fock states, which now I put quotes on the Fock states, are going to be the eigenstates of this integrable Hamiltonian. I'll call those Fock states, right? Of course, they've got a lot of detailed structure associated with solving the integrable problem, right? So they're really only Fock states in quotes, right? But that's just what I'll call them. And because right, and then we have this term which will scatter between Fock states like before, right? But now the geometry of this Fock state is much less clear, right? And so you might ask, which M are the near neighbors to N? So if I want to scatter from N to some other Fock state M, before I knew which were the neighbors, right? I changed just 4 of the occupation numbers, whereas now most of these integrable systems and the types of integrability breaking terms you would add, those things aren't well known, right? And the technology to understand the geometry of this eigenstate space as defined by matrix elements of an integrability breaking term doesn't seem to be developed in integrable systems. So if there's anybody here who does integrable systems, I'm presenting a challenge to you that would be very nice if someone could make more progress on this. Okay, so generally, so we've looked at this numerically. So because, first of all, we're not integrable systems professionals, and we're asking a question that even the professionals don't seem to know the answers to. So we just did numerics. We took small integrable systems and broke the integrability and looked at the matrix elements of the perturbation. And what you find is essentially all pairs of eigenstates of the integrable system are coupled by this perturbation, right? If I just have it be a randomness term. And break all the conservation laws other than the energy, right? And so that says this scatters every state to every other state, right? And so that doesn't help define a geometry, right? Just asking, does it scatter? It doesn't help, okay? So what we decided to do, which seems to make sense, is to let the strength of the matrix element define the distance. So if we ask how far apart are Fock state N and Fock state M, which are eigenstates of the integrable Hamiltonian, given this integrability breaking parameter, we will use that matrix element to define that distance. So large coupling means they're nearby, and small coupling means they're far apart. Right? And so we just rank the distances. So this sort of defines a distance, doesn't satisfy triangle inequalities, so it's sort of a weak sense of a distance. And as I said, unfortunately, the statistics of this have not been obtained other than what we did, which is numerically for small systems. And I just put this question out there: can the technology of solving integral systems, which is highly developed for many questions, be developed to get the answers to these questions? We've talked to a few people, and it doesn't seem to be around yet. Okay, so what I'm going to do is I'm going to define Z of NU. So I have my integrable system, say it's got N spins in it, and then U is a matrix element, as I'll say, and Z is a coordination number. So this is the number of neighbors.
Excuse me, I have a comment.
Yeah, go ahead.
Yeah, so in integrable system, actually, there is a way to compute this kind of matrix element in the name of a form factor technique. So basically, all this integrable system has a factorized systems, so that we know that they satisfy Yang-Baxter equation, etc. Now, so since we know that eigenstate of this eigenstate, or your name of the Fock space, and if you introduce any operator U, it doesn't matter whether they are preserved or not, any operator, then it's a matrix element between two scattering states can be computed explicitly. Or exactly.
So if I use that to define a distance, can you then understand the geometry of this space?
Actually, how to define the distance in your
well, it's the distance is monotonic in the matrix element. Well, okay. So I'm going to tell you what you need for this calculation, and you can think about whether this really is feasible. We haven't actually found an integrable system and an integrability breaking parameter where the information we need for this calculation can be obtained analytically, or in a way that's not, all we did is just brute force exact idealization, not really using the technology. But I'm just putting this out here as a challenge. I'm not saying this can't be done. Okay, so the way we organize this information is we pick a matrix element, magnitude U, and we say the coordination number at distance U is how many other states. So we pick one state N and ask how many other states have a matrix element UMN that's of order U. So let's say between U over 2 and 2U, right? So that's just saying, and we're going to call those all at roughly the same distance. And there are Z of them. I call it Z because it's like a coordination, right? And that will depend on U, and it will depend on the size of the system N, right? And these are the kinds of statistics we want. Is what's this number as a function of U? Okay, and then we ask, does this system delocalize by these couplings, right? So now we have this Fock space, we have a distance, and we want to ask, does it delocalize by hopping over distance U, right? So if we go at distance U, matrix element U, then the matrix element is G times U, and the level spacing is 1 over Z, right? Because there are Z levels and they're spread out over an energy of order 1. And then we just need to compare this to ask, will it delocalize or will it stay localized, right? So here it is again. There's our integrability Hamiltonian, the coupling constant. We add the integrability breaking. There's the matrix element. And here's a state. And we ask, does it delocalize to this near continuum? And the level spacing is that. And so this gives that the critical value for delocalizing for size n and matrix element u goes as 1 over u times the coordination number. And then for a given n, we have to ask, where is this minimum? So the system will delocalize using the u or distance that minimizes this or maximizes this, right? And so what happens is if you look at very large u, z goes to 0, right? Because there's a maximum value of this matrix element, right? And so if u is too large, z goes to 0 and this goes to 0, right? If we go to very small u, z, what happens at small u is u goes down faster than z. So this also goes to 0 at very small u, because there are matrix elements that are very far away in Fock space and they're exponentially small. And so this quantity u times z has a maximum somewhere in between. And the examples we looked at, so we looked at a lot of different examples. So I'm not saying this is general, but for a bunch of examples we looked at, which we talked about in that paper, from numerics, not from analytics, we find that the delocalization, which occurs at the maximum of this, occurs at a u and a z that are powers of n, not exponential. And therefore, it's short-range hopping in Fock space, very analogous to the gas example I did earlier, right? And so this is our conjecture based on just these ideas and some numerics. And as you know from doing, we're talking about exact idealization numerics, the system sizes are very small. And so, the numerics just are consistent with this conjecture. They don't really motivate it particularly or confirm it particularly, right? But our conjecture is integrability breaking. So adding a perturbation and breaking integrability is generally a Fock space delocalization phase transition in a non-thermodynamic large system limit, like what I told you about in this gas example, where you have to take the coupling to 0 as a power of the volume of the system. And in that limit, there is this Anderson localization type transition from a near integrable phase where the integrability breaking was too weak to delocalize the eigenstates in the basis of the eigenstates of the unperturbed system, and then there's a delocalization transition where it thermalizes. So that's yeah.
Okay,
Yeah,
so
go ahead.
You introduced some generic perturbation U here, but intentionally one may choose some special U that does not breaking the integrability. For example,
Yeah.
in the XXG
Yeah, no, we don't want to do that.
Yeah, you don't want to do that, but
I don't want to do that.
I mean, to test whether this program is working or not, just taking the Z component interaction out of this XXG chain, okay? So I have a XXG chain, which is beta-tangent integrable. And then I take this Z interaction as a perturbation U here, okay? And then you do the same calculation. You can estimate this coordination number. Then what do you expect if I choose this wrong U perturbation, which does not break integrability?
Well, I don't know yeah, I don't know that you would see anything different. I have, but certainly, we want to add a perturbation that does break the integrability.
So if you introduce integrability,
I don't think this proposes a way to test whether a particular right. What you're asking is, I add a particular perturbation and I want to know, does it break the integrability or not? Right. Whereas here, I think we're assuming it does break the integrability, and we're estimating at what coupling constant does it break the integrability, and how does that scale with the system size? But I don't think, since this is really just done to first order in the perturbation, I don't think the information would be there to test whether you've really broken the integrability. Right. If you put in a term which didn't break the integrability, even when it was strong, it wouldn't necessarily show anything different.
But still, you can measure this coordination number.
Yeah, right. No, you could go through this whole exercise for a case that doesn't break the integrability, yes. But I'm not sure what you'd learn from that.
Okay, I see. And you mentioned there are a few examples which show this kind of, in the next slide, you mentioned so many examples from numerics. And did you?
Well, we were looking at various ways of breaking,
Do you also consider
standard integrable models like XXZ, say put a random field or a staggered field, or and some cases that are Jordan-Wigner. You also have systems where they're integrable and become non-interacting, but only with a Jordan-Wigner transformation, and we looked at those as well.
Did you also consider single impurity as a perturbation U? You just
well, that could be right if it breaks the we didn't look at any cases of single impurity, but I think a single impurity would be a fine way of breaking the integrability.
And there were some works,
and those might be easier things to work with, in terms of getting this information.
Okay. Yeah. Thank you.
No, I'm partly putting this out there as a challenge to the people who really know how to do these integrable systems calculations, right? Because we're sort of not asking for so much. We're just asking for first order matrix elements and their statistics. Go ahead. Was there another question?
Yes. So let's consider 2D Ising model, and with the T different from TC, and introduce external magnetic field. And it is well known that if you have both perturbation, it's non-integrable. If you introduce only one perturbation, like a T is different from TC with the H external magnetic field is 0, then it's integrable. It's just a massive Majorana Fermi theory. And if you introduce T equal to TC and H different, then this is a well-known Jamolotchikov EA scattering theory. So both cases are integrable. But if you introduce both parameters, it's non-integrable. Excuse me, hello?
Yeah.
Yeah. So let's consider the simpler case that the T is different from TC, but H is very small, just away from H equals 0, very small. Then what is your conjecture corresponding to?
That in a finite size system, there will be a threshold value of that field that's very small and goes to 0 as we take the limit of a large system. And that transition in that, if we take the limit that way, so you take the field to 0 in the appropriate way as you take the system to infinity, staying away from the critical point, so staying away from Zamolodchikov, that there will be a Fock space or a Fock space delocalization transition between a regime where
but my feeling is that
the field you've added is too small to break the integrability and make the system thermalize, and a larger field regime where it thermalizes. Now, we're not really talking about 2D Ising model. We're really talking about the 1D quantumizing.
Yeah, exactly.
Talking about a quantum system.
It's 1D quantumizing.
Yeah.
It's
Quantum system. Yeah.
Yeah. It's quantum system, 1D spin chain.
Yeah.
And now
so that ETH will only emerge above a certain strength of that field. And the strength of that field where the ETH.
My feeling is that your conclusion is based on something like quantum mechanical point of view, that the basic
absolutely.
freedom
Absolutely.
is not changing. But in quantum field theory, actually, as I said, the single fermion theory is totally changing. It changed into totally different scattering theory, where there are 8 particles instead of the single Majorana fermion appear. There are very non-trivial phase transition between the massive Majorana theory to EA scattering theory. So
that's also integrable, right? So we don't want to be talking about a case where
each line is integrable, but in the intermediate range is non-integrable.
Yeah. Okay. Yeah.
So
but this would be just moving from one integrable system into the non-integrable system. That's
right.
With a small perturbation.
Yeah. So you are considering just near this single.
Near one of them and just a small perturbation. Yeah.
Okay. Thank you.
Yeah. Okay. So I've used up a lot of my time. So let me quickly go through the other topic, which is thermalization in Floquet systems. And so this I'll just go through quickly just to give you a flavor of what so we have this paper here. This is my student, Ellen Morningstar, Vedika Kamani. This is on the archive. And the question is, what thermal in quotes, equilibria do Floquet systems go to? So now I'm talking about a Floquet system, periodic in time Hamiltonian. And I write this as the time average of the Hamiltonian plus a term that's varying in time. It has a time average of 0. Right? And this term is now not small. The way I make its effect weak is not by having it be small, but by having it have a short period or oscillate at high frequency. Okay. So my system, let's say it has n qubits. We're doing finite n, but much bigger than 1, same spirit of what we had before. Talk about a finite system, but consider the limit. And let's say both of these terms just contain 1 and 2 spin terms. So these are just local. Okay. And and now the Floquet unitary that gets you advances the system by 1 period is e to the minus I, the integral of the Hamiltonian. Here now I've got h bar equals 1, and then you have to make sure this is done in a time-ordered way. Okay, so that defines the Floquet unitary. And what we want to do is we want to find a quasi-local, time-independent, effective Hamiltonian that best approximates this exact unitary. So we want to approximate this unitary as best as we can with e to the minus I, the period times the time-independent Hamiltonian. Now, in this point here, I want my system to be chaotic. H naught is chaotic, so everything's chaotic, and we're just all we're asking about is there an effective Hamiltonian which is extensive and is conserved, or is energy only conserved modulo the frequency of the drive? Okay, so what do I mean by quasi-local effective Hamiltonian? What I mean is it's only got few spin terms. The high spin terms their total contribution is falling off exponentially. So if we have n spin terms, their total contribution falls off exponentially with n. So it's effectively a local Hamiltonian. It's got tails, but that's okay. Now, like before, okay, so now we're going to work in the basis of the eigenstates of this best approximation for the Floquet operator. And when people experimentally make Floquet systems, what they're sometimes trying to do is actually make a particular effective Hamiltonian, right? So this is the thing they're trying to make, right? And then the question is have they done that, or is the system actually going to heat up? Is it going to absorb energy from the drive and not actually conserve this energy, right? Okay, so if we work in the basis of the eigenstates of this effective Hamiltonian, what we've got is the Floquet operator isn't exactly this. There's some deviation, which gives matrix elements, which cause transitions between the energy being E effective and the energy being E effective plus omega or minus omega, because two states that differ in energy by omega of H effective have almost the same eigenvalue of the Floquet operator, right? Because E to the I T omega is just 1, right? So the process we're talking about here is the system absorbing or emitting one photon into the periodic drive and changing its energy by omega, right? And so again, we have a similar consideration to what we were talking about before. Compare the matrix element to the many-body level spacing. Now here, this is all the states at this energy. So these level spacings are exponentially small in the size of the system. And now, so with this discussion, we have two regimes of Floquet thermalization that I want to talk about. One is the no heating regime, where the matrix elements of the Floquet operator between eigenstates of this effective Hamiltonian are much smaller than the many-body level spacing. And this happens at high frequency or small period drive or small enough systems. So this level spacing is large. And in this condition, the system does not absorb Floquet photons. So I call them Floquet photons. It's just absorbing or emitting an energy omega, I've said h bar to 1, to the drive. And so in this regime, this effective Hamiltonian is conserved. The system thermalizes to an equilibrium defined by that effective Hamiltonian as if it was a time-independent Hamiltonian, and it is extensive. And then there is a transition, I'll argue later, that it happens at again, in a non-thermodynamic limit, where the limit you take now is, as I take the system to infinity, I take the period of my drive to 0, or I take the frequency of my drive to infinity in order to get into this regime or to see this transition. And then beyond the transition, what we get is weak heating. Now the matrix elements are bigger than the many-body level spacing, and the system does absorb or emit Floquet photons at a rate gamma, which is non-zero. Here, this rate is 0. Here, it's non-zero. And so what happens in this regime is this putative, extensive Hamiltonian with an energy. It's only conserved modulo omega, and it's only conserved to precision gamma, right? Because if this transition is happening at rate gamma, it'll broaden the lines here by gamma. Just Fermi golden rule kind of idea.
Question. Existence of question. Yeah, existence of H effective proven. So in this Floquet system, so you rewrite
not well. Sometimes there is no useful, right? There are examples where, well, first of all, you can just do perturbation theory at high frequencies, right? So you just treat this perturbatively at high frequencies. That's called the Magnus expansion. And so that gives you a systematic estimate of H effective.
Yes.
And so but it's only an asymptotic expansion, right?
Yeah.
And the statement is, if we do a finite system and we're in this no heating regime, that expansion actually converges and H effective really does exist. But if we're in the weak heating regime, there really isn't an H effective that exactly matches the Floquet operator. It only is a good approximation, right? And so the best H effective still doesn't capture these processes of absorbing and emitting photons to the drive, right?
So sorry, can I ask a question?
You go ahead.
Yeah, so I was a little confused about the last slide. So I would have thought that higher frequency drive would usually suppress the heating because it's resonant.
No heating is small tau, which is high frequency.
Oh, okay. I see.
And if I go to lower frequency, I can get heating. Yeah.
I see. Sorry.
So I just maybe said it unclearly.
So, and I see, because you're dealing with finite size system, you can have regimes where no heating absolutely happens, even if T is in. If I wait. Okay, I see. That's
there are there are models where you go through this calculation. There are states at energy E, between E and E plus omega, but the level spacings are much bigger than the matrix element, and so there's no heating. Although those states are there, but they just don't couple because. And then as you go to either a bigger system or a longer period, lower frequency, you can have this transition at this point. J is the microscopic energy scale in H effective to this weak heating regime. And then what happens in the weak heating regime, you can, if you look at the support of the eigenstates of the Floquet operator in terms of the eigenstates of this best H effective, it can look like this. So here's E effective. And then we have these peaks spaced by omega, and each peak has a width gamma, and the states here, say like if I started over here, these states can decay to these states by absorbing 1 omega from the drive, and then these can transition over to here, and these can transition to here. But what happens if it's a spin, right? There's a highest energy and a lowest energy, and there's a certain energy which corresponds to infinite temperature where there's the highest density of states. And so it typically looks like this, that the system heats up. It doesn't strictly heat to infinite temperature. It heats to high temperature, high positive temperature, and high negative temperature. And it's at energies spaced by omega. They don't necessarily coincide with infinite temperature. And it's not at all energies. Really infinite temperature would be all energies equally likely. Whereas here, that's not what you have. You have a set of energies spaced by omega, right? So people often say when a Floquet system heats up, it just heats up to infinite temperature. But it's really not true. There's a big regime where the line width here, gamma, is much smaller than omega, and it heats up to this distribution, which is an unusual thermal equilibrium distribution. You haven't seen that in your statistical mechanics course. So this is we're calling this Floquet ETH. When you have heating, you get a Floquet ETH where the eigenstates of the Floquet operator are thermal in the sense they have maximum entropy. And when we look at them in the basis of the eigenstates of the best H effective, the entropy has been maximized, but given the constraint, and there's the constraint, they conserve the energy modulo omega. So they can't be at any energy. They have to only be at energy spaced by omega, and it's only to precision gamma. So you end up with this distribution being the maximum entropy distribution, satisfying these constraints. And that's what the system goes to. And we've checked this in various models, again, numerically. On the scale of size systems you can diagonalize. So this is a new type of microcanonical equilibrium, right? It's microcanonical in that it's fixed energy, but it's only fixed modulo omega, because you have the drive and the system can change its energy by omega, but not by other amounts of energy. And because it is changing, it has a certain imprecision. H effective is not perfect, right? Now, if the line width is bigger than omega, then this really gives infinite temperature, right? These lines just all these peaks overlap with each other, and all states are populated, right? And so that's what happens if you have a Floquet system at large N and also low frequency drive or a large period. And if you have both of these or one of them strongly enough, you actually really do get infinite temperature. But there's this big intermediate regime where this is what the equilibrium looks like. And that's something which didn't seem to be appreciated until our paper.
David?
Yeah.
Yeah. We have already 1.5 hours.
Yeah.
So I just want to remind you. Okay.
Yeah. Okay. So let me just finish up. Okay. So one interesting case of this is where you take the limit of a large system and small period, but n times tau big enough so you're in this weak heating regime, and the line width is narrow compared to omega, and then you pick two energies, one at positive temperature, one at negative temperature, so infinite temperature is halfway in between, and these two energies have the same entropy, then the equilibrium ensemble will be 50% probability here, 50% probability here in the limit of a large system. And so it's an interesting thing. We're at a very high temperatures. There's no, we're at very high temperatures. If I start my system with this energy, under the Floquet drive, it will go to an equilibrium, which is 50% probability at this energy and 50% probability at this energy. So it spontaneously develops a long-range order in its energy density or its local temperature, even though it's at very near infinite temperature. So it's a rather striking thing to happen at such high temperatures. So that was one of our discoveries. Okay, so let me, okay, so there's a nice paper by Abanin Daruk Huveniers 2017 showing how these line widths or heating rates depend on the drive frequency. So I was going to tell you about that, but let me just skip to my conclusions since the time is up. So I discussed two dynamical transitions that occur in non-thermodynamic large system long time limits. One is integrability to chaos and thermalization. This is a Fock space delocalization, delocalization transition, or at least we know that's true for non-interacting systems adding interactions, and we conjecture that that's true rather generally for integrability, adding integrability breaking perturbations. And then the other case I talked about, without showing you all the details, is chaotic Floquet systems that have a transition between the non-heating phase, which has a conserved extensive H effective and has a temperature, et cetera. And then the heating phase where H effective is only conserved modulo omega and only to some precision gamma. And this phase here has this new type of Floquet microcanonical equilibrium when the heating rate is small enough. That's actually in some ways rather different from infinite temperature. People usually say when the Floquet system heats up, it just heats up to infinite temperature. but that's not really correct. It heats up to a novel equilibrium that's near infinite temperature, but it's not exactly infinite temperature. It's something, it has a bunch of other structure. Okay, so that's what I wanted to tell you.
Okay, thank you very much.
Sorry for.
So, yeah. Any questions or
Yeah,
comments?
any more questions?
Yeah, I have a question. Thank you for your nice lecture. I know that there is some work by Cardy some years ago about some quantum quench problem, that although you start with a certain integrable system, you can summarize it by acting some quenched Hamiltonian, such that eventually it evolves into summer states. So do you have any comment on this, related to your
Well, for me, a quench is just an initial condition.
Right. Yeah. So you prepare
and then during the time evolution, what's the Hamiltonian, right? And what you're describing, I think, is something where the Hamiltonian during the time evolution after the quench, it's not an integrable Hamiltonian.
It can be integrable Hamiltonian too, no? You mean, of course,
well, okay.
State is not eigenstate of the Hamiltonian.
Yeah, right. So we have to be careful. So I was defining, right? So, even with integrable systems, they thermalize to a generalized Gibbs ensemble, right?
Well, that's always possible.
And that type of thermalization, I wasn't talking about. So when I said thermalization, I mean not to a generalized Gibbs ensemble. I mean to a real, to something where there's only a few conservation laws. So there is thermalization within integrable dynamics, which is discussed, and I think that's what you're referring to. But that's not what I'm talking about. So I'm assuming we have broken the integrability.
So this quench is always related to generalized Gibbs ensemble?
Well, I don't know about always. If the dynamics is given by a Hamiltonian that's integrable,
Hamiltonian,
and then you say it thermalizes, it's really thermalized to some generalized Gibbs ensemble.
Okay.
Because it has an infinite number of conservation laws, and whatever your initial condition was, it's still there. Is those conservation laws still have the same value.
So you think that this generalized Gibbs ensemble is a not real thermodynamic system? Or how do you accept this?
No, it's just a different situation. It's not quantum chaotic, right? It's a different situation.
Okay, thank you.
Anybody else?
So I have another question. So when we apply some integrability breaking field to the integrable system, then usually the system remains away from equilibrium for a long time, which is called pre-thermalization time.
Yes.
And after that time scale, the system approach to the real thermal equilibrium state. And
yes.
In this localization, delocalization transition picture, can you have some expectation for the scaling behavior of this pre-thermalization time scale?
Well, this is where so you have pre-thermalization that lasts, right? If you have a small but non-zero integrability breaking term, then you have a long pre-thermal regime, and then it ends and the system thermalizes.
Yes.
Right? And then as you approach this transition I was telling you about, that time scale diverges.
Yes. How fast?
And then there's a regime in the finite size systems where the pre-thermal regime lasts forever.
Last forever.
Yeah. So if you go
For
to,
finite size system, you mean?
yeah, if you take the limit, as I said,
Mhm.
let's go back here. Sorry. Where did I have it? Here.
Mhm.
So in this regime here, this is basically pre-thermalization lasts forever.
Mhm.
So it requires, as you take a large system, you take the coupling smaller,
Mhm.
the integrability breaking term smaller,
Mhm.
and you can take this limit. So
Mhm.
there is a phase here
Mhm.
where the integrability is slightly broken, right?
Mhm.
So we're not in the same eigenstates as the integrable system. They're a
Mhm.
little bit perturbed,
Mhm.
but not delocalized in Fock space.
Mhm.
And the system is pre-thermal forever.
Forever.
The
Okay.
eigenstates are pre-thermal. Whereas over here, the pre-thermal regime would last some very long time, but then eventually would thermalize, like you said.
Mhm. And then actually this thermalization time diverges as you approach to this.
As you approach this
threshold,
point here,
like one.
yes. Yeah.
And do you have some theory for the divergence of this time scale approaching this point, for example?
Yeah, that's basically in here. So this is Anderson localization in a high dimensional, high coordination number, basically beta lattice type geometry.
Mhm.
Random graph geometry with a high coordination number.
Mhm.
Yeah, so there's a time scale which diverges. I assume with a power law, but I'm not positive about that. But that would probably be in here.
Okay, I see. Okay, so are there any?
Yeah, it's basically Anderson localization and the limit of high dimensions.
So I think I couldn't catch the last part where you, I believe, computed the distribution at weak heating regime. Could you? So how did you?
Well, not computed, I showed.
Okay, so how did you? I think I couldn't catch what's.
Yeah, so we, an eigenstate of the Floquet operator has an eigenvalue, which is on the unit circle, right? And that corresponds to energies of the effective Hamiltonian that are only defined modulo omega, right? Because, this e to the I tau times an energy, if I increase tau times the energy by 2 pi, I come back to exactly the same value, right? And so you have these different values of the energy that all correspond to the same eigenvalue of the Floquet operator. So in the energy, this, and this, and this are not degenerate. They differ by omega or multiples of omega. But in the Floquet operator, this is wrapped around the unit circle, and this, and this, and this, and this are all degenerate because they're at the same point on the unit circle of the eigenvalues of the Floquet operator, right? And so that's why it's like a microcanonical situation. It's microcanonical for the eigenvalues of the Floquet operator, but because, e to the I tau times e equals something has multiple solutions, right? When you take the logarithm of a complex number, there are multiple answers, and that corresponds to multiple energies, which are all degenerate with each other in the spectrum of the Floquet operator, right?
Okay.
And so you end up with this unusual sort of microcanonical equilibrium, which is it's basically energy constrained modulo omega to some precision, right? And then you maximize the entropy. So this peak is stronger just because there's more states here. Here there are fewer states. Here there are fewer states. Here there's even fewer states, right?
And then, and then probably in the next slide, you were talking about this.
And so this would be a case where I've made it so there are two peaks which each have half the probability. If I take the limit of a large system, the next peak over here and the next peak over here will have negligible probability compared to these. And then I can tune it so these two have the same probability, and keep that situation as I take the limit. And that makes this, sort of unusual equilibrium ensemble, which has two different temperatures.
And what do you mean by spontaneous, like long range order? Like what kind of long range order?
Well, if I start with this energy, the system will, with probability a half, absorb one photon and go over here. Or it will stay here with probability a half. And these are well separated, right? So if I look at any degree of freedom in here, I'll see, oh, it's at this temperature, which is positive in this part of the wave function. Whereas if I look in this part of the wave function, it has this temperature, which is negative, right? So it's sort of like a Schrödinger cat state, or you could say it's got long range order in its energy density, right? Because these differ in energy density.
I see, interesting.
So
Okay,
the system has, really all it's doing is it's either absorbing a photon from the drive or not absorbing one from the drive, right? And they happen with equal probability. But those two peaks are far enough apart that they're distinguishable, right? So it's sort of a spontaneous formation of a Schrödinger cat-like distribution that happens just as the system goes to equilibrium at very high temperatures.
I see.
Just because it's driven at a very high frequency. So the difference between it's a small enough system driven at a high enough frequency, so the energy difference from absorbing one photon really changes the temperature.
Right. So it's kind of that number n and omega have the same. I see.
But this is a regime, in the systems people are building now with, qubits and, this is a regime which is very close to being accessible. We actually had a lot of discussions with experimentalists as to whether they could observe this, and it's just very close. But, I think this is something which, within 5 years or so, people will be able to take systems and do this. We were hoping they could do it this year. We had a bunch of discussions with people, and all the people we talked with, they were just almost there, but not quite in their current systems. Or maybe we just didn't talk. Maybe we just didn't talk to the right people.
I see. Yeah, thank you very much.
Yes,
we could make a simple model with just 20 spins on and make this happen in a in exact idealization in a way that would be observable. Yeah, you can see that in our paper.
Okay, so are there any questions from the audience?
Yeah, it's time for me to go to bed.
Yeah, I think this is the right time to wrap up this session. So let's thank the speaker again. Thank you very much for this wonderful presentation.
Thank you very much, Professor David Huse and also Professor Dongno. Yeah, thank you very much. Yeah.
Okay. Good night.
Good night. Bye.